That thing we did on Wednesday required us to know the population variance. What if I don't? Well, then all I really have is my sample variance. And that means I don't have sigma, I have S. The variance is S squared, I'll have the standard deviation. This time it'll be the sample standard deviation instead of the population standard deviation. But that means I don't actually have a known variance. I can't claim normality. I have to deal with the fact that that unknown population variance means I can't use my Z table. If I can't use Z, I'm back in the same boat I was with confidence intervals. When I was building a confidence interval and all I had was the information from the sample, I used T instead. And that T distribution means I also need degrees of freedom. Somebody remind me. How do I get degrees of freedom?
It's n minus 1.
Aha. So I get it from my sample size. Everything else we do parallels exactly what we did Wednesday. So what I'm going to do is I'm going to set up a one tail or a two tail. I need to know what my null hypothesis is. I need to know what my alternate hypothesis is. Instead of finding a Z calculated value, I will find a T calculated value. And that's going to be my sample average minus my benchmark divided by the standard deviation over the square root of n. The same standard error. The only difference now is instead of sigma, it's S. It's the exact same formula with one change. That right there. And that means that instead of a Z critical value, I have a T critical value. Now, in this case, I am far more likely to use my tables and not use a p-value unless I'm in technology. Because when I go back and I look at my t-table is very limited. My t-table only contains particular critical values. It even says so right here at the top. And since finding P involves looking stuff up in a T distribution, I don't have the full T distributions here. But I have the commands to do T distributions in Excel. I have the commands to do T distributions in my calculator. So I can get a P value from technology. I can't necessarily get it from my table. The process works the same. Problem 37. The manufacturer of Glow More flat white interior latex paint claims one coat coverage of 400 square feet per gallon on interior walls. A painter keeps careful track of 6 gallons and finds coverages in square feet of 360, 410, 380, 360, 390, and 400. So they say I can get 400 square feet of painted surface. In the last 6 gallons I've used, those are the numbers I have. They claim 400. Based off of that, are they right? They claim 400. That's my benchmark. I have 6 samples, 360, 410, 380, 390, another 360, and 400 dead on. Some of my gallons definitely were 400 square feet or higher, but some of them were smaller. I need to ask a question before I do any other calculation. My null hypothesis here if I go back and I read this text carefully, the manufacturer claims one coat coverage of 400 square feet per gallon. Are they saying exactly 400 square feet? At least 400 square feet? No more than 400 square feet? So that I know what kind of a test I'm doing, I have to decide how we're writing the null hypothesis. Leo.
Would it be equal to 400? That would be not equal to 400.
It doesn't say anything about less than or greater than in here. So maybe that's the right way to go with equals. That'd be a two-tail test. On the other hand, if you think about a painter saying, I should be able to get at least 400, it would have been nice if they used those words. I could do a one-tail test, but I think their words say a two-tail test is better. So that's what I'm going to write down right at the beginning so I know what kind of a test I'm doing. I am testing the null hypothesis is that my average is 400, and the alternate hypothesis is that it isn't. Now that means the average might actually be bigger than 400, might be smaller than 400, I can't tell. It's just not 400. With me so far? So, I need 2 pieces of information. I need to know what sensitivity I'm doing this test at. It says here in the textbook, at alpha equals 0.1, does this evidence contradict the claim? The claim in question is our null hypothesis. So I want to know, should I reject at 0.10? I now need 2 pieces of information. I need my calculated value. I need my critical value. I can get the critical value fairly easily. It specifically on this table differentiates one tail from two tails. And notice the columns are just lined up with one tail having 5%, two tails will have 10%. With one tail having 10%, two tails will have 20%. So they've lined it up, so I only need to look at one setup. I wanted alpha equals 10. Which number do I need for my critical value?
It would be the 0.1, but then it would give you 2.015 because the DFN minus 1.
My degrees of freedom come into play. I had 6 samples. My degrees of freedom is 5. So the critical number I want is 2.015. If I had chosen a one-tail test, if I had read this as I can get at least 400 square feet per gallon, then instead of using 2015, I'd use 1476. Now I need a calculated value. To get the calculated value, I need 2 other things. Scroll back up. I need my sample average and my sample standard deviation. Because I can't do this formula without that piece of information. So, grab your calculators. Let's do the descriptive statistics. If you've got Excel open, type in that list and do the standard deviation and the average there. Stat, edit a list. Let's put in these numbers: 360, 410, 380, 390, another 360, 400. There's my list. And now I can go stat calculate. The descriptive statistics is the one variable statistics for that list. There's my average. There's my standard deviation. 383.3, 20.66. Remember, I'm using the sample standard deviation, not the population standard deviation. And now I can calculate my t-score. 383.3 minus 400 over 20.66 over square root of 6. Value for the top divided by that standard error. I'm going to go ahead and call that negative 1.98. So I've calculated my statistic. I have a critical value to compare it to. Do I accept or reject the null hypothesis? You've done the work. But this is the important part. Make the decision.
We should see if the T-calc is bigger than T-crit, but with the, I don't know how to put it in.
The absolute value
The
bars.
absolute value.
Is that true or false? Is the calculated value in absolute value bigger than the critical value?
It's smaller.
1.98 would be the absolute value here. 1.98 is smaller than 2.015. And that means we cannot reject. I only reject when that answer is yes. And that means this evidence does not contradict the claim. As far as this pile of 6 gallons of paint is concerned, any variability here was just up to randomness. Questions? Yes, Hassan.
If it wasn't like if it wasn't a 2 days exercise, I just changed the value of the crit
Yes,
and that's it, right?
correct. Now, with 5 degrees of freedom, there's the T-crit we had with a 2-tail test. There's the T-crit we have with a 1-tail test. If I change from 2-tail to 1-tail, my answer changes. If I did a 1-tail test, then I would be saying that my null hypothesis would be mu bigger than or equal to 400. And the alternate hypothesis would be strictly less than 400, be one side, right? And as a 1-tail test, this evidence doesn't support the claim. If we switch from 2-tail to 1-tail, we actually reject the null hypothesis. So our choice, our reading of their statement makes the difference here. Leo, you said to me, the way the sentence is read, it says they get 400 square feet. So I said equals.
Yeah.
But if I read, they get at least 400
That'd be
square
greater
feet.
than or equal to.
And that would be a 1-tail. And in this case, this average is too small for a 1-tail test. So it is absolutely important for us to say the reason we read the null hypothesis, wrote the null hypothesis the way we did, was because of the way we read the problem. And our phrasing of the problem can affect our answer there. Now, you could actually get a p-value. If you go into Excel you're going to have to look up this number in the t-distribution. So in Excel, I need a 5 somewhere in here. Hang on. I think that's one. It's 5, comma 5, comma 1. Let's open Excel and check. Equals T dot DIST parentheses. Yes. X, then degrees of freedom, then 1, because I want the CDF. So negative 1.98, comma 5, comma 1. And I get 0.052. That's less than 10%, right? But if I'm doing a two-tail, what do I have to do to that number?
Multiplied by 2.
Which would make it 10.4%, which is bigger. See the difference? My choice of test changes my answer here. Now, I can do this entire process in Excel. There's my paint samples. So I take their average, standard deviation. There's my benchmark. There's my calculated value. It's the same formula. Average minus benchmark divided by standard deviation divided by the square root of the count. I had to type in the formula longhand. There it is. And then there's my p-value. That p-value, again, is for a one-tail test. If I'm doing a two-tail, I got to multiply by 2. If I was doing a right tail test instead of a left tail test,
Or minus.
I'd use 1 minus because I'd want the area above as opposed to the area below. Questions? Since P is bigger than alpha, I don't reject my null hypothesis. If I was doing a one-tail test, then I would have. Question. I already put this information into the calculator, right? It's in this list here. Under edit, there's my data. Like I said earlier, the calculator will do this same test. Under distributions, sorry, no, it's under stat again. There are my tests. And I'm doing a t-test, not a z-test, because I don't have the population standard deviation. So I go to my t-test. When we were doing these before, I could give it the statistics, right? I could tell it, this is the average, this is the standard deviation. I can put those numbers in. But I can also say, hey, the data I want is in list L1. Then I don't have to bother to figure out the mean and standard deviation beforehand. My benchmark, on the other hand, this is the benchmark from our previous version. The last T thing we did had an average of 3.5, right? So it's still remembering that number. I have to change that to be 400. And then I have to tell it which kind of test I'm doing. We did a two-tail. Calculate. And there's my p-value. More decimal places means instead of doing 0.0523, it came out a little different, rounded differently in different places. 1.976, we gave it 1.98. That's why we got a different value. Average, standard deviation, n. It came up with that same t-value we did. And it came up with the same p-value. I like this. Questions? Just look at the settings we have these problems phrased in. We just talked about paint coverage. The average weight of a package of rolled oats. Okay, quality control, right? Those are really the same question. Am I getting the claimed amount of coverage from the paint? Am I getting the right amount in the package? Mean purchase price of a smartphone. We go to 20 different business managers and ask them how much they paid for their phone. Average age of a part-time seasonal employee. Did it change from 37 years to the new one, which is now 38.5? Is that a significant change? Number of entrees purchased in a single order. Mileage per lease. Why do I give it? That's a legitimate question to ask. Why do I care? Does anybody here like chocolate chip cookies? Okay, good. I want you to Google something for me. Google Chips Ahoy statistics. I'm pretty sure you'll get a news article. Does anybody know the slogan for Chips Ahoy cookies? It was printed on every package of cookies for probably 7 or 8 years, if not longer. Anybody find the news article? Do a Google search, click on the news thing at the top. The slogan used to read, "1,000 chips in every bag." So a group of high school students asked if that is true. Here's what I'm saying. And they went out and bought 24 bags of Chips Ahoy cookies and washed away the cookie part just so they could leave the chocolate chips behind and counted them and ran a t-test and then gave the information to the manufacturer. Because the evidence they gathered did not support the manufacturer's claim, 1,000 chips in every bag. They changed the tagline on the cookies so they didn't get sued. Isn't that the stupidest thing you've ever heard of? Consumer quality assurance. Sounds dumb. But if you make a claim in your business, you have to be able to back it up. Question. I can take the same idea and make it serious instead of lighthearted. I want to know the average number of contaminants per chocolate bag. Did you know that there is a legal limit, a maximum threshold for non-food particles in food? If you go buy a box of cookies, the flour they use might have a rock in it. Be a very small rock. Made it through the milling process of the flour. But that could get baked into a cookie. And you could bite down. And that would suck. But there's a legal limit. So I will take a bag of flour from your manufacturer and I will sift it and I will examine what is food in there and what isn't. And as long as it is less than 0.01%, I'm good. If I have a 100-kilogram bag of flour, 0.01%, 10 grams. If you take a standard water bottle, plastic half-liter bottle, and fill the cap twice, that's roughly 10 grams. That's a lot of rocks in my flour, isn't it? Question. I would point out to you that what I just gave you, though, as a benchmark, was a proportion, not an average. I gave you an average with a known standard deviation and an average with an unknown population standard deviation. What happens when I go to test a proportion? Well, now I'm comparing the population proportion to my sample proportion. This is where it starts to get annoying because I'm going to use the same letter P to mean two different things. I apologize, I didn't come up with this crap. I have to deal with the labels they've given me. In some textbooks, you will see that the p-value we've been using, when we're talking about the p-value we got at, is sometimes called p with a hat. You'll actually see it written this way. That's the probability one. This is our proportion one. I keep getting confused because different pieces of software reverse those sometimes. So depending on what software I'm using, it's gonna with me. I don't like that. So I apologize. But realistically, proportions are far more common than averages. I'm testing market share, retention rate, return on investment, preference, right, between A and B, like or dislike. If I have my sample statistic the number of people who prefer product A is X out of my sample N, then my test statistic should be based on what I think the population is. So I'll need a benchmark for the population. I'll have some benchmark proportion. And I'll be able to ask the same question. Should I do a right tail test, a left tail test, or a two tail test? Do I think that my sample proportion is equal to, greater than or equal to, less than or equal to? I can do the same setup. But this has to be assumed or estimated somehow. We did confidence intervals for proportions. When we did confidence interval for proportions, what distribution did we use? This is in the homework I just gave back to you. You should look.
It was normal.
Was normal. Means I'm using Z. Get rid of T, put in Z. And that means I'll have a Z calculated and a Z critical. Now, I have to go back and remember the formula we used for our confidence interval. Because what I need is the denominator. My Z calc is going to be my sample proportion minus my benchmark. And then I have to divide by the standard error for a proportion. When we did the standard error for a mean, that was the X divided by the square root of N. But when we do it for a proportion, this is different. And we got it by doing that square root. Let's see, it was number and then 1 minus number, and then it was divided by N. That's our standard error formula. And if you go back and you look in section 8, in the homework I just gave back to you, you'll see that was what we did to find the margin of error for our confidence interval. But everything else, again, plays exactly the same rules. If I'm doing a proportion, don't need this table anymore. I need my normal table. I need my normal values that we were already doing. So I have the same idea. In a hospital shipment of 3,500 insulin syringes, 14 were unusable due to defects. Insulin syringes are really thin needles. They're 30 gauge or smaller. For the record, piercing earrings are usually 16 gauge. Most standard earring backs are 18s. So imagine that you get something substantially thinner than an earring back. That's a really, really thin needle. It's easy to bend. It's easy to, when you cut the needle to length, it's easy to crimp the tip. I don't want to stick that in my arm if it's going to rip something. So I don't want to use a bad needle. The hospital's quality standard is no less than 99.7% of the needles can be usable. Off the bottom of the screen, you can't see what I'm writing. If 99.7% of the needles must be good, then how many of them can be bad?
Would be 0.3.
Percent, right? So this number up here is counting defects. 14 needles were defective. So I'm going to go with this as my benchmark, the 0.3%. Because that's counting the same thing. So they tell me at alpha equals 5%, should I accept or reject batches from this manufacturer from now on? Did they give me too many defective needles? Too many. This is a one-tail test. My null hypothesis. Everything is cool, and the proportion will be less than or equal to 0.3%, which is 0.003. I'm going to keep taking your needles because this is just one bad batch. I really should expect you guys to normally be making this cut line. What's my alternate hypothesis?
It would be greater than 0.3%.
Right. So the alternate hypothesis is greater than, that is a right tail. Okay. Same setup. I need a Z-calc. I need a Z-crit. Fortunately, the critical value is an easy lookup because I know my alpha value. And that's on the list of numbers I gave you earlier in this week. I have an 0.5 for alpha. What is the critical value for Z? One tail. Bing! 1.645. If it was two tail, I'd be using 1.96. If it's one tail, it's 1.645. And now I do my Z calculate. I take my proportion, P. I didn't work out my proportion. What is my proportion? Oh, that's 14 defective needles out of 3,500. I subtract my benchmark, 0.003. And then I divide by my standard error, which is 0.003 times 1 minus 0.003, which is 0.997, over 3,500. $14 over 3,500. 0.004. So this is a very small top, but it's an even smaller bottom. And when I'm all said and done, I get 1.08-ish. Do I reject or not?
We don't,
Because
because P hat is not bigger than P.
my cutoff is 1.64 and I'm a 1.08. The rejection region for a right tail is way out to the right, so I'd have to be beyond my cutoff. I'm not there. What does that mean for my supplier? There's my null hypothesis right there at the top of the screen. I did not reject that. This batch of needles does not contradict this statement. As far as I am concerned, this supplier provides good needles. This one batch was out of line with their typical production. Or at least I don't have evidence to say, you guys, your needles suck, you need to fix this. If I have the ability to go through and say, hey, I'm going to reject this shipment rather than this whole batch, this whole manufacturer for the rest of the time, well, then I'll return this one shipment and say, guys, you got to do better. Now, the problem with insulin syringes and medical devices in general is that they are usually sealed. They're autoclaved and sterilized, and they're sealed. So to test them, you have to open them up. Oops. If I'm opening them up, I'm going to begin using them. Well, if I ran through 3,500 needles and found 14 defects, I'll be annoyed. I'll call the company and say, hey, this was a hinky batch. You guys should do some quality investigation. A type 1 error here, false positive, means I would reject an acceptable set of syringes. And that means people who need insulin syringes would go without. What happens when you don't have enough syringes? Either you don't take your insulin, that's bad, or you reuse a syringe, which can cause infections. Equally bad. A false negative means I take a shipment that I shouldn't have. And people get hurt using defective syringes. A defective syringe can break in your body. That will require surgery. Let's not do that. How do I get a p-value for this? Leo?
Would be X over N, so it would be
Uh,
14.
That's this number right here. That's the proportion. How do I get the probability, the p hat value? The probability value.
Is it the one minus that value of the chart?
Aha. So the probability that z is bigger than 1.08, which is 1 minus the probability that z is less than 1.08, that I look up on my chart. And that number I can do off my normal distribution, and that is 0.1397, which is bigger than 0.05. This is yet another confirmation I should not reject the null hypothesis. Questions? More on Monday. I'll see you all then. Have a wonderful rest of your day.